One of the most emblematic features of biological aging is telomere attrition, the gradual shortening of the protective DNA caps at the ends of chromosomes. Telomeres act like buffers, preserving the integrity of the genome during each cell division. When they become too short, cells enter a state of senescence or undergo programmed cell death. This process has been widely cited as a key marker and even a driver of aging, often framed as inevitable, a molecular clock ticking down toward dysfunction. But this metaphor, though appealing, obscures an essential truth. Telomere shortening is not merely an internal countdown. It is profoundly influenced by the nutritional environment of the cell. Indeed, the stability and repair of telomeres depend heavily on nutrients involved in methylation, antioxidant defense, and DNA synthesis. In this light, telomere attrition is far less of a pre-programmed failure and much more of a consequence of chronic deficiency. At the center of telomere maintenance is the enzyme telomerase, which can add base pairs back to telomeres and help maintain their length over time. Telomerase activity, however, is sensitive to nutrient status. Key components of one-carbon metabolism, such as folate, vitamin B12, and choline, are required to support the methylation processes that regulate gene expression, including genes controlling telomerase. If these nutrients are lacking, methylation patterns become erratic or incomplete, leading not only to impaired telomerase function but to genomic instability across the board. This doesn't simply increase the pace of telomere shortening, it reduces the cell's ability to protect and restore its DNA architecture altogether. In addition, telomere replication demands the same cofactors required for general DNA synthesis and repair. Iron and zinc are essential for the function of DNA polymerases and repair enzymes. Without sufficient iron, cells struggle to complete proper DNA replication. Zinc is a critical structural component of DNA-binding proteins and plays a central role in maintaining genome fidelity. When these minerals are deficient, DNA replication becomes less efficient and more error-prone, and telomeres become collateral damage in the larger process of compromised cellular renewal. Furthermore, oxidative stress directly accelerates telomere shortening, as telomeric DNA is particularly vulnerable to damage from free radicals. The guanine-rich sequences of telomeres are hotspots for oxidative attack, which can cause breaks and impede replication. Nutritional antioxidants like vitamin C, vitamin E, selenium, and polyphenol help buffer this damage, yet these compounds are often underconsumed or depleted in populations with high stress or inflammatory burdens. Without sufficient antioxidant support, the telomeres are essentially left unguarded, subjected to daily chemical erosion that is both preventable and measurable. This understanding challenges the idea that telomere attrition is simply biological aging in motion. It reframes the process as conditional, responsive to the quality of nutrient availability and metabolic balance. Indeed, population studies have consistently shown that individuals with higher intakes of folate, B12, zinc, and antioxidants tend to have longer telomeres and slower biological aging rates, even after adjusting for age. Conversely, chronic deficiencies in these nutrients are associated with accelerated telomere loss, increased inflammation, and earlier onset of age-related disease. What this suggests is both empowering and urgent. Telomere integrity is not merely inherited, but nourished. It reflects decades of cellular exposure to adequacy or scarcity. Rather than seeking telomerase activators in the form of pharmacological interventions, we might achieve far more sustainable results by ensuring that the nutritional prerequisites for telomerase activity and DNA repair are continuously met. Moreover, this deficiency-driven view of telomere shortening aligns with the broader picture of aging as cumulative malnutrition. Just as mitochondrial dysfunction, impaired proteostasis, and oxidative damage can arise from unmet nutritional demands, so too does telomere erosion. These are not separate stories. They are multiple expressions of a single underlying reality, that life depends on a steady stream of specific, measurable biochemical resources, and that aging is, to a large extent, what happens when that stream begins to trickle rather than flow. In this light, telomere-based aging is not a ticking time bomb, but a feedback mechanism. It signals that the cell's needs are going unmet, particularly in its most vulnerable functions: replication, repair, and genome stability. This means we are not powerless. Folate, B12, zinc, iron, selenium, and antioxidant-rich foods are not exotic compounds. They are everyday nutrients that can be prioritized, protected, and intelligently replenished. Ultimately, When we stop viewing telomere attrition as fate and start seeing it as a solvable deficiency, the paradigm shifts from inevitability to opportunity. Aging becomes not a countdown to dysfunction but a call to action. Nourish the cell, protect its genome, support its defenses, and the decline slows. And in many cases, function can be restored, not by fighting time, but by feeding life.